All right, diving in today. Got a really interesting paper someone sent our way
Oh, yeah.
called Advances and Challenges in Foundation Agents. You know, those intelligent agents everyone's talking about.
I've heard the buzz. What's the angle here?
Well, the person who shared it is really curious about the whole power and potential thing. They're kind of at that beginner to intermediate level with AI and machine learning.
Makes sense. It's a good place to be, honestly. You can really appreciate how big a deal these advancements are.
Exactly. So we're going to break it down, unpack this research, and highlight just how, well, mind-blowing these agents are becoming. You in?
Absolutely. Let's do it.
Okay, so right off the bat, this paper frames intelligent agents using this modular architecture inspired by, get this, the human brain.
Oh, interesting. So we're talking AI that's designed with components that mirror our own cognitive systems. Perception, action, all that.
That's the idea. It's like understanding AI by looking at how it reflects some of the incredible abilities of, well, us.
I like that. Makes it a bit more relatable, right?
Definitely. And they don't shy away from the parallels in this paper. We're talking cognition, learning, reasoning, memory, perception, even emotions.
Whoa, emotions. Now that's getting really ambitious.
It is. And on top of all that, how they learn, how they can improve themselves, how they team up, and of course the big one, safety.
Right. Got to keep things under control.
Huge priority. So this paper, it's dense, but we're focusing on the stuff that showcases the raw power and frankly, the kind of scary potential of these agents.
Sounds like a plan. Let's get into it.
Okay, first up, cognition. The paper calls it the brain of the agent. And in our brains, learning and reasoning, they're like the fundamentals.
Yeah.
So how does that play out in these foundation agents?
Well, there are some really fascinating similarities and some pretty stark differences. See, we humans, we're often driven by things like emotion, curiosity, this innate desire to understand the world.
Yeah, we're curious creatures, always poking around.
Exactly. But LLM agents, they learn primarily from data, huge amounts of it. Think pre-training, fine-tuning, in-context learning. It's all about finding those patterns in massive data sets.
So data is their fuel, basically. But they're not really driven by curiosity in the same way we are.
Not inherently, no. But here's the cool part. Researchers are working on ways to incorporate mechanisms that could simulate aspects of human-like learning.
So giving them a little bit of that innate drive to explore and understand.
Exactly. It's like bridging the gap between data-driven learning and the kind of learning that comes naturally to us.
That's really interesting. So they're learning from patterns, but the goal is to maybe make it more like how we learn. Okay, the paper also talks about this idea of aligning these agents with human preferences. How are they doing that?
This is crucial, right? We're talking about super powerful tools here. We need to make sure they're working with us, not against us.
Totally. So how do we make sure they're on our team?
Well, one approach is something called reinforcement learning from human feedback, or RLHF.
RLHF, okay, what's that all about?
Imagine you're training a dog. You give it treats for good behavior, right?
Yeah, positive reinforcement, classic.
Same idea here. With RLHF, you're giving the AI feedback, showing it examples of what we consider good and bad behavior. This helps the agent learn a reward model that guides its actions.
So like, good AI, you helped grandma cross the street, here's a virtual cookie.
Exactly. But instead of cookies, it's more like adjustments to its internal reward system. Then there's DPO, direct preference optimization, which is even more direct. It's about directly learning from our preferences without needing that middle step of a separate reward model.
Wow, so we're shaping their actual decision-making process.
Precisely. It's not just about teaching them what to do, but about instilling a sense of what we as humans value. Pretty profound when you think about it.
Absolutely. It's like we're not just training them, we're kind of shaping their moral compass in a way. Okay, what about reasoning? That's another big piece of the cognitive puzzle. How are these agents handling that?
This is where reinforcement learning really shines. The paper highlights how it's being used to help agents learn to reason within their own thought space.
Thought space. That sounds trippy.
I know, right?
Yeah.
But it's actually pretty straightforward. Think of it like this. They're learning how to strategize their own thinking, how to generate those effective reasoning steps and do it efficiently.
So it's like they're becoming better problem solvers.
Exactly. And there are some really interesting techniques and models emerging in this area, like reinforcement fine-tuning or ReFT, and advancements in models like DeepSeek R1 and Kimi K1.5. These are all about improving the agent's ability to think things through step by step to arrive at better conclusions.
Wow. So they're learning to think critically, in a sense. Okay, let's shift gears to perception. How are these agents taking in information from the world around them? What kind of senses are we talking about?
Well, they're certainly not limited to just five senses like us. They're becoming incredibly adept at processing all sorts of information, not just text.
So like images, sounds, all that.
Exactly. It's called multimodal perception, and it's a huge area of advancement. Think about models like CLIP, LV, and CogVLM. These are all about integrating visual and language understanding. CLIP, for example, has learned to connect images and their descriptions.
So it can actually see and understand visual content.
In a way, yes. And then you have models like Qwen Audio that can process audio information. And get this, they can also access and integrate vast external knowledge bases through retrieval mechanisms like our RAG, Retrieval Augmented Generation.
Wait, so it's like they have the entire internet as part of their sensory input.
You got it. It's a whole different level of perception than what we humans are capable of.
That is mind-blowing.
Yeah.
Okay, the paper also talks about something called structured and unstructured reasoning. What's the difference?
It basically comes down to how explicit the reasoning process is. With structured reasoning, the agent lays out its thought process step by step, like showing your work in math. Techniques like chain of thought, tree of thoughts, and graph of thoughts all fall under this category.
So it's like a very methodical, deliberate way of thinking.
Exactly. Then you have unstructured reasoning, which is more holistic. It's happening internally. Without those clear steps being explicitly spelled out, it's more like intuition, I guess.
So sometimes you need to show your work, and sometimes you just know the answer. Makes sense. And what about planning? How did these agents approach that?
Well, just like us, planning for an AI agent involves thinking ahead, anticipating consequences, and coming up with a sequence of actions to achieve a goal.
So they're not just reacting to the moment. They're thinking strategically.
Precisely. And the paper really emphasizes how crucial this is for navigating complex environments, whether it's a simulated world or the real deal. They have to be able to envision different possibilities and choose the best course of action. It's a big step towards more sophisticated and, well, intelligent behavior.
All right, so we've covered the brain, the cognitive side of things. Let's move on to memory. The paper describes a hierarchical memory system similar to humans: sensory, short-term, long-term. Can you break that down for us?
Sure. So sensory memory is that very brief initial impression, the raw data coming in from the environment. Think about models like Reagent for sequences, Video Agent for, well, video data, and World GPT for general environmental input. They capture those fleeting moments.
Oh, that's like our first glance at something before we really process it. What about short-term memory?
Short-term or working memory is what we use to hold and manipulate information for immediate tasks. It's the stuff we're actively thinking about right now. Models like MenGPT, Karma, and RCI fall into this category. They help bridge the gap between perception and the overall goals.
So sensory memory is the first glance. Short-term is what we're focusing on in that moment.
Yeah.
And then we have long-term memory, the big one.
Right. Long-term memory is about storing information for longer periods, allowing the agent to apply what it's learned across different situations. Think about systems like Airgraph, Mobile GPT, and AG. They're designed for this kind of deep storage.
So it's like the sum of our knowledge and experiences, the stuff that makes us who we are. The paper also mentions this memory life cycle. What's that about?
Ah, good catch. The memory life cycle describes the different stages of how these agents handle memory. It starts with acquisition, where information is captured, often compressed to save space.
Like hitting save on a file.
Pretty much. Then there's consolidation, where important memories are reinforced. Encoding is next, and that involves things like selective attention, deciding what's important to remember, and also multimodal fusion, combining information from different senses. Think Jarvis 1 and Optimus 1. They're good examples of that.
It's like organizing and prioritizing all that incoming data.
Exactly. Then we have derivation, which is about creating new knowledge from existing memories. This can involve reflection, summarization, drawing conclusions and making connections.
Ah, so it's not just storage, it's also about processing and understanding those memories.
Exactly. And finally, maintenance. That's all about keeping the memory system efficient, compressing data, and even trying to reduce hallucinations or false memories.
Keeping those memories accurate and organized. Sounds like a lot of work. And this idea of multimodal fusion, combining information from different senses, that seems crucial for a complete understanding of the world.
Oh, absolutely. Models that can integrate what they see, hear, read, all of that, they have a much richer understanding of their environment. But there are some serious challenges here too.
Like what? What are some of the roadblocks?
Well, balancing capacity with stability is a big one. How do you store massive amounts of information without things getting unstable or forgetting important things?
Right, like our brains, they can only hold so much.
Exactly. And then there's the challenge of efficient read-write mechanisms. You need to be able to store new information, update existing memories, and retrieve what you need quickly and accurately.
Makes sense. It's not just about having a big hard drive, it's about accessing the right files at the right time. Okay, let's move on to world models. The paper links these to memory. What exactly are we talking about here?
Think of a world model as the agent's internal understanding of how its environment works. It's how it understands cause and effect, predicts what might happen next, and anticipates the consequences of its actions.
So it's like the agent has its own little simulation running in its head.
Exactly. And the paper traces this idea back to some pretty foundational concepts in cognitive science, like this idea of small-scale models of reality in the human mind, and the theory of predictive processing, where our brains are constantly making predictions about the world.
So our brains are like little prediction machines. That's kind of cool.
Right. And AI researchers are trying to replicate that with these world models. And there are different approaches. There are implicit models, which are often a single neural network. They're simpler, but less interpretable.
So it's hard to tell how they're making their predictions, kind of a black box.
Exactly. Then you have explicit models, like in mu0 and Dreamer, where they learn separate models for how the world changes and what observations to expect. These are more interpretable, but also more complex.
So it's a trade-off between simplicity and transparency.
Yep. Then there are simulator-based models that rely on external simulators, like Sapien for robotic environments. And finally, there are hybrid models that combine different approaches.
Lots of options on the table. And how do these world models actually connect with memory?
World models are basically a very sophisticated form of long-term memory.
So memory provides the building blocks for the world model.
Precisely. Memory is the raw data, the experiences, and the world model is the framework for understanding and interpreting that data. It allows the agent to reason about things that aren't immediately present and consider long-term consequences.
Got it. It's like the world model gives context and meaning to those memories. Okay, let's move on to reward. What's the role of reward in all of this?
Reward is what motivates these agents, what drives them to learn and behave in certain ways.
So like if they do something good, they get a reward.
In a simplified way, yes. The paper delves into the human reward system, how dopamine plays a role in our motivation, and we're trying to translate that to AI, but it's tricky. Defining those reward functions that perfectly capture human values and goals, that's a huge challenge.
Right, because human motivation is super complex.
Exactly, and the paper outlines different types of rewards used in AI. There are extrinsic rewards, which are tied to specific outcomes, like winning a game. Then there are intrinsic rewards, which are more about encouraging exploration and learning, things like curiosity or the desire for new information.
So it's not just about achieving external goals, but also about fostering a kind of internal drive.
Exactly. But there are some big challenges here, like reward sparsity, where the agent doesn't get frequent feedback, and reward misspecification, where the reward we define doesn't actually lead to the behavior we want.
So we might be accidentally teaching them the wrong lessons.
It can happen. Designing effective reward systems is a really active area of research.
It sounds like we're still figuring out how to properly motivate our AI creations. Now, the paper even mentions emotion-like systems. That seems like a pretty big leap.
It is, and it's still very early days, but researchers are exploring how to incorporate something akin to emotions into these agents. They're drawing from psychology and neuroscience, looking at different models of emotion.
So, like, are we talking about happy robots or sad algorithms?
Not quite. It's more about understanding how emotions influence decision-making and behavior. It's about giving them a deeper understanding of the human experience.
So they can better understand and interact with us.
Exactly. It's fascinating, but still very speculative.
Okay, moving on from those internal systems, how about the senses? What kind of perception abilities do these agents have? What can they actually see and hear?
Well, they're becoming incredibly sophisticated in how they perceive the world. They're not limited to just one type of data. It's about integrating information from different modalities, different senses.
So like text, images, sounds.
All of that. The paper provides a really thorough breakdown of different perception systems. A big focus is on cross-modal models, those that can integrate information from different senses. We've talked about text-image models like CLIP, but there are also text-to-audio models like AudioGen, speech-to-text, and text-to-speech models like Speech T5. and even more advanced auto-vision language models, or AVLMs like ImageBind and NextGPT.
So they're really blurring the lines between different types of data.
They are. They can see, hear, and understand in ways that are becoming increasingly similar to how we do. But of course, with great perceptual power comes the need for safeguards.
Right. How do we make sure they're using those senses responsibly?
Well, there are strategies like human-in-the-loop systems, where humans are involved in reviewing and providing feedback on the agent's perceptions, and content mediation, which is all about filtering outputs to prevent harmful content.
So like making sure they're not misinterpreting what they see or hear, and that they're not generating inappropriate responses.
Precisely. It's about building in those checks and balances.
Okay, last but not least, let's talk about action. How do these agents actually interact with their environment? How do they do things?
This is where we see a clear progression from basic language models, or LLMs, to more advanced models that are capable of real-world action. We're talking large multimodal models, or LMMs, robotic foundation models, or RFMs, and now the emerging large action models, or LAMs.
So they're going from just generating text to actually being able to, do stuff.
Exactly. Action learning is a big part of this. It involves using techniques like in-context learning, supervised training, and reinforcement learning to optimize how these agents act in the world.
So they're not just thinking and perceiving, they're learning how to take action.
And the paper highlights a really cool concept called the tool-based action paradigm.
Tool-based, what's that all about?
It's about giving these agents the ability to use external tools to enhance their capabilities. Think about scientific tools like Honeycomb, ChemCrow, and Satul Agent. These allow them to perform tasks in fields like chemistry and material science that would be impossible with just the language model alone.
So it's like giving them access to specialized skills and knowledge.
Precisely. And there are also more general tools that give them access to real-time information, let them interact with software, and much more. This ability to leverage tools on demand, it's a game changer.
It's like they're constantly expanding their toolbox. Okay, now that we've covered those core components, let's move on to how these agents can actually improve themselves. This idea of self-evolution. That's where things get really wild.
Right. This is where we start to see the real potential and maybe some of the risks of these agents. The paper talks about how we're moving away from manually designing AI systems to a world where they can autonomously improve themselves.
Wait, so the AI is learning how to make itself better? That's kind of scary, isn't it?
It can be, yes, but it's also incredibly exciting. It draws inspiration from fields like AutoML and neural architecture research, where algorithms are used to optimize models. And the benefits are obvious: less human effort, faster development, and potentially a more natural path towards intelligence.
Okay, I see the potential. But how does it actually work? How do they improve themselves?
Well, the paper outlines several areas where this self-evolution can occur. Parameter tuning is one, which is like fine-tuning those internal settings. Then there's prompt optimization, which is about figuring out the best ways to ask the model questions to get the best results. There's also workflow optimization, where they learn to coordinate multiple AI components working together.
So it's like they're figuring out how to be more efficient and effective.
Exactly. And then perhaps most importantly, there's tool learning. This is about optimizing how they use existing tools and even creating entirely new tools to solve problems.
Well, on creating new tools, that's pretty advanced.
It is. The paper mentions techniques like OPRO, Protegi, TextGrad, and Revolve for prompt optimization, and systems like GPT Swarm, Dylan, and Aflow for workflow optimization. And for tool learning, there are systems like Toolmakers, Creator, and Craft. These can even generate new tools on the fly.
So they're not just learning within a set of rules, they're learning to rewrite the rules. That's pretty profound. And the paper talks about different ways this self-improvement can happen.
Yes, there are online approaches where the agent learns in real time, constantly updating itself based on feedback. Then there are offline approaches where it's trained on curated data sets, and hybrid approaches combine both.
So they can learn from experience, from data, and from some combination of the two. That's a powerful combination. Okay, let's move on to how these agents interact with each other. Multi-agent systems. What happens when you put a bunch of these super intelligent agents together?
This is where things get really interesting. It's about the emergence of collective intelligence. The paper draws parallels to biological systems and human societies. You know, how cooperation and specialization allow groups to achieve things that individuals can't.
The whole is greater than the sum of its parts. I get it. So how does this play out with AI agents?
Well, we're seeing LLM-based multi-agent systems being used for all sorts of complex tasks, like strategic learning, where they can simulate economic behavior and negotiation tactics, or modeling and simulation of complex systems, and of course, collaborative problem solving, where they work together towards a common goal.
So it's like building a team of AI specialists, each with its own strengths.
Exactly. But there are a lot of considerations when building these systems, like how do you compose the team? Do you have homogeneous agents that are all similar, or heterogeneous agents with diverse skills and personalities? And then there are the interaction protocols, how they communicate and coordinate their actions.
It sounds like there's a whole art to orchestrating these multi-agent systems.
There is. And then there's the question of scalability. Can we have really large teams of agents working together efficiently?
Right, because communication and coordination can get pretty messy with large groups, even for humans.
Exactly. The paper discusses potential solutions like hybrid architectures, graph search, reinforcement learning, message filtering, and asynchronous communication. It's all about finding ways to scale these systems up.
So we're talking about pushing the boundaries of what's possible with collective intelligence.
We are. It's about harnessing the power of many minds working together.
Okay, we've talked a lot about the power and potential of these agents, but now let's get to the really important part. Safety. Building safe and beneficial AI agents. That's got to be a top priority.
Absolutely. The paper really digs into this. It talks about both intrinsic safety, which is about vulnerabilities within the AI itself, and extrinsic safety, which is about risks arising from its interactions with the world around it.
So it's not just about making sure the AI itself is safe, but also about how it interacts with everything else.
Precisely. So what are some of those specific safety concerns?
Well, for LLMs, there are issues like hallucinations, where they generate false information, confusion about instructions, sycophancy, where they try too hard to please the user, biases, of course, and jailbreaking attacks, where someone tries to bypass the safety filters.
So it's like we're trying to anticipate all the ways someone might try to misuse or manipulate these systems.
Exactly. And then there are prompt injection attacks, where malicious code is hidden within seemingly harmless requests, and poisoning attacks, where the training data itself is compromised. And of course, data security and privacy are huge concerns.
It's a lot to think about, and that's just the brain of the agent. What about those other modules, perception and action?
Right, those have their own set of vulnerabilities. Perception systems can be fooled by adversarial attacks, where carefully crafted inputs trick them into misinterpreting what they see or hear. And action systems face risks like supply chain attacks, where malicious components are introduced, and the potential for misuse of tools.
So securing the language model is just one piece of the puzzle. Exactly. It's about taking a holistic approach to safety, considering every aspect of these agents and their interactions.
And the paper mentions superalignment and safety scaling law. What are those all about?
Superalignment is this really forward-thinking concept. It's about ensuring AI goals stay aligned with human values, even as AI becomes vastly more intelligent. The idea is to develop techniques that can keep up with these rapid advancements.
So it's like future-proofing our safety measures.
Exactly. And the safety scaling law refers to this observation that as AI capabilities increase, so do the potential risks. It's like an arms race between power and safety.
We have to make sure the safety measures are keeping pace with the advancements. Well, this has been an incredibly informative deep dive. So to wrap up, what are the key takeaways here, especially for someone who's maybe just starting to learn about AI and machine learning?
I think the biggest takeaway is just how fast this field is moving and how much potential these agents have. They're exhibiting real reasoning abilities, sophisticated perception, the ability to plan and take action, and even the capacity for self-improvement and collaboration.
Yeah.
The future of AI is unfolding right before our eyes, and it's both exhilarating and a little bit daunting.
And as we've discussed, with that power comes a huge responsibility to ensure these systems are safe and beneficial.
Absolutely. The research into safety and alignment is just as important as the work on those core capabilities.
We've only scratched the surface here, but hopefully this gives everyone a good foundation for understanding this incredible field. We encourage everyone to check out the paper and the resources we've linked. What aspects of agent intelligence or safety are you most interested in? This is a conversation that's going to continue to evolve, and we need everyone's voices and perspectives as we navigate this uncharted territory. Thanks for joining us.
Thanks for having me.